So here we give some examples of matrix spaces. So example 1. So consider R, comma D1. Where R, this is the set of reals, and D1, this is a function from R cross R to R. This is distance function, R cross R to R, defined by D1 x comma y. This is equal to absolute value of x minus y, where note that where R, for little r in the set of DLs, this is equal to R if R is greater than or equal to 0, and minus R if R is less than 0, R belongs to R. Okay. So this is absolute value function. Then it is straightforward to check that. It is straightforward to check that D1 is a metric on R, and thus D1, so this order pair, a matrix space. So basically one needs to check D1 x comma y, this is greater than or equal to 0 for all x comma y in R. With so absolute value, this is always greater than or equal to 0. So this is always greater than or equal to 0 for all x comma y in R, and d x comma y, this is equal to 0 if and only if this is equal to 0, and therefore x minus y equal to 0. That is if and only if x equal to y. And secondly, one needs to check d1 x comma y. This is equal to this is equal to absolute value of x minus y, which is equal to absolute value of y minus x, and that is equal to d1 of y comma x. And lastly, to check the triangle inequality, that is d1 of x comma y, this is less or equal to d of x comma z plus d of x z comma y. So this happens for all x comma y comma z in R. Now this is also true for absolute value function. So this is a metric space. D1 is metric on R, and this metric D1 is called the Euclidean metric on R. Okay, so this is called the Euclidean metric on R. So there might exist many other matrices on R, but this one is called Euclidean metric on R. So next we give example of discrete metric space, example 2. So here we consider X an arbitrary non-empty set at X not equal to empty set B, let be arbitrary. Then we define D from X Cartesian product with X to R, defined by D of X comma Y. This is equal to 1 if X not equal to Y, and 0 if x equal to y. So x is any non-empty set. Okay, we define d by this, then x comma d is a matrix space. Again here, one needs to check these three conditions, and and so by definition of D, so it is straightforward to check. For example, for first axiom, D of xy, this is either 0 or x. So 0 when x equal to y and 1 when x not equal to y. So this is always non-negative, either 0 or 1. So this is always non-negative, and equality holds if and only if x equal to y. And d of xy, so when x equal to y, then d of xy equal to 0, and d of yx, that is also equal to 0. So d of xy equal to d of yx. And when x is not equal to y, then both the values d of xy and d of yx are 1. So they are equal. And for triangle inequality, so d of xy, that is equal to that is equal to either 0 or 1, and d of x comma z plus d of y comma z. Okay, so that is either either. Okay, so let me write the triangle inequality: d of x comma y, this is less or equal to d of x comma z plus d of, so this is third axiom for distances. So y, so this is z comma y, and we have written z comma y. So if x is not equal to y, so if x is not equal to y, then at least one of x comma x and z, or z and y, they must be not equal. So left hand, if x not equal to y, then left hand side is equal to 1, and right hand side must be at least 1. Okay, and when x equal to y, then left hand side is 0, so right hand side greater than or equal to 0. So here triangle inequality holds true. Okay, so this is a matrix space x comma d. So where d is defined here, this is a matrix space. So x is the underlying space, and this special metric d, this is called discrete metric. So this is called, D is called discrete metric on X, and this metric space is called discrete metric space. Called a discrete metric space. So on every non-empty set, we have at least one metric which is discrete metric. And now we give third example. In third example, basically we extend our example 1 from R to Rn. Okay. So example 3, Rn d1 and d1 from Rn cross Rn to R is defined by R. And well, this Rn is the set of all n tuples of reals x1 and so on xn belongs to, so this is n tuple such that xi belongs to R for all I equal to 1 and so on n. This is Rn. And this function is defined by, let me define here, d1 of x comma y. So well, let's say x equal to x1 and so on xn n tuple, and y equal to y1 and so on yn. So yi, these are real, so it belongs to Rn. And d1 of x comma y, this is equal to summation xi absolute value of xi minus yi and summation over I equal to 1 to n. Okay, and more explicitly this is equal to x1 minus y1 plus and so on plus xn minus yn absolute value of this, and this is a metric space. So let us check three axioms of distances for this D1. Okay, so for any real numbers xi and xj, xi minus xi and yi. So xi minus yi absolute value of this. So xi and yi, these are real numbers. So xi minus yi, this is also real. So absolute value of any real number that is greater than or equal to 0. Okay, so finite sum of non-negative real numbers of I equal to 1 to n. This is again non-zero. So this is again non-negative. Okay, so that is, so what is the left hand side? This is nothing but d1 x comma y. This is greater than or equal to 0, and equality holds d1 of x comma y. This is equal to 0 if and only if the summation xi minus yi summation over I equal to 1 to n, this is equal to 0. Sum of non-negative reals that is equal to 0 if and only if each summand that is equal to 0. So if and only if xi minus yi, so absolute value, this is equal to 0 for all I equal to 1 and so on n. And this is if and only if xi equal to yi for all I equal to 1 and so on n. And this is if and only if x equal to y. Therefore, d1 of x comma y equal to 0 if and only if x is equal to y. So this is the first axiom for distances, which satisfied by the function d1. Now we show commutativity. So x equal to x1 and so on up to xn, comma y equal to y1 and so on up to yn belongs to Rn. So every real numbers xi and yi, so xi minus yi has absolute value same as absolute value of yi minus xi, and this is true for all I equal to 1 and so on up to n. And therefore, if you take summation on the both side, then again they are equal over summation over I equal to 1 to n. I equal to 1 to n. And so this implies, so left hand side is nothing but d1 of x comma y is equal to the right hand side, which is nothing but d1 of y comma x, and this is true for all x comma y in Rn. So this is commutativity. Now we show triangle inequality. Let us take another point, z equal to z1 and so on zn from Rn. Then for now we know that for every real numbers xi minus yi has absolute value less or equal to xi minus zi plus absolute value of zi minus yi, and this is true for all I equal to 1 and so on up to n. And so this implies the summation over I equal to 1 to n of absolute value of xi minus yi is less or equal to absolute value of xi minus zi summation over I equal to 1 to n plus zi minus yi absolute value of this summation over I equal to 1 to n. Now, and therefore this implies, so this left hand side is equal to d1 of x comma y is less or equal to, this is equal to, so d1 of x comma z plus d1 of z comma y, and this is true for all x comma y comma z in Rn. Okay, so therefore triangle inequality is satisfied by the function d1, and therefore we conclude that therefore Rn comma d1 is a metric space. So next example, that is example 4. So here again the underlying space is Rn, and we define another distance function on Rn. So Rn comma d infinity, where d infinity from Rn plus Rn, where this is defined by d infinity of x1 and so on, xn, comma y1 and so on, yn. So this is equal to maximum of absolute value of xi minus yi over I lies between 1 and n. So again, this is a metric. So let us check 3 axioms for distances. So xi minus yi, this is again greater than or equal to 0, and this implies max of non-negative quantities, non-negative reals. This is again greater than or equal to 0, max over I equal to I lies between 1 and n, and this implies d infinity x comma y. So this, let's say this point is x and this point is y. So this is greater than or equal to 0, and equality holds d infinity x comma y, this is equal to 0 if and only if max xi minus yi over I lies between 1 and n, this is equal to 0, and this is if and only if xi minus yi has absolute value 0. So this is if and only if xi equal to yi for all I equal to 1 and so on up to n, and this is if and only if x equal to y. So equality holds here if and only if is x is equal to y. For the second one, second axiom, xi minus yi, so this is equal to yi minus xi, and therefore max of these are equal. I lies between 1 and n. I lies between 1 and n, and this implies dx comma y, this is equal to dy comma x. For triangle inequality, so z equal to, let's say z equal to z1 and so on, zn belongs to Rn. Then what we know is xi minus yi is lesser equal to xi minus zi plus zi minus yi, and this implies xi minus yi has absolute value, xi minus yi has absolute value lesser equal to max xi minus zi plus max zi minus yi. Okay, so and I lies between 1 to n. Now right hand side is a fixed real number, and this is true for all I equal to 1 and so on to n, and therefore this implies max is also less or equal to the right hand side, xi minus yi I as between 1 to n is less or equal to, so this is nothing but d infinity x comma z, and second term this is nothing but d infinity z comma y. That's also, and here the left hand side this is equal to d infinity x comma y. So this is left hand side is less or equal to d infinity x comma z plus d infinity y comma z. Okay, so this is example 4. Now we give another example where the underlying set is the same, that is Rn, and therefore that is we will define another metric on Rn. So example 5, Rn comma d2, where d2 from Rn cross Rn to R is defined by, to consider, where this function is defined by d2 of x comma y, this is equal to xi minus yi whole square summation over I equal to 1 to n whole power half. So again here it is easy to check non-negativity of d2 or positive definiteness of d2 and commutativity of d2. So namely, let us check xi minus yi, this is always greater than, square is always greater than or equal to 0, and therefore summation of this over I equal to 1 to n, this is always greater than or equal to 0, and now whole power half, this is greater than or equal to 0. So note that a square square root of a square, this is equal to mod a. So this is definition. Okay, so this is always greater than or equal to 0. This implies d2 of x y, this is greater than or equal to 0, and with equality if and only if, now d2 of x comma y, this is equal to 0 if and only if xi minus yi square summation over I equal to 1 to n, this is equal to 0. So this is nothing but sum of non-negative reals. Left hand side is sum of non-negative reals which is equal to 0, and this is if and only if xi minus yi, this is equal to 0 for all I equal to 1 and so on up to n, and this is if and only if x equal to y. Okay, therefore equality holds if and only if x is equal to y. So here equality holds if and only if x equal to y. So now for commutativity, xi minus yi, this is the second condition, square, this is equal to yi minus xi square. This is true for all I equal to 1 to n. Therefore we take summation over I equal to I equal to 1 to n, I equal to 1 to n. So this is all again equal. Therefore, power half, this is also equal. So, so this implies d of xy equal to, so d2 of xy, this is equal to d2 of y comma x. This happens for all x comma y belongs to Rn. Now for triangle inequality, so third, now we prove triangle inequality, which the proof of triangle inequality, which is so called Cauchy-Schwarz inequality in Rn. Cauchy-Schwarz inequality in Rn. So first we prove Cauchy-Schwarz inequality in Rn. So let me state it as a theorem. For x equal to x1 and so on, xn, comma y equal to y1 and so on, yn, in Rn, we have x comma y, this is called inner product. And absolute value of this inner product is less or equal to norm of x times norm of y. So where inner product x comma y, this is equal to xi times yi, and summation over I equal to 1 to n, and this is equal to inner product x comma x whole power half. So this is called Cauchy-Schwarz inequality in Rn. So now we prove this theorem. Proof. So we consider two cases. Case 1. So in case 1 we consider x and y are linearly dependent. So for x and y in Rn, either x and y are linearly dependent or independent. Are linearly dependent. And in case 2, we consider case 2, let me write, consider x and y are linearly independent. So in case 2, we consider linearly independent. And so when x and y are linearly dependent, then there exists, then this implies there exists are some real number such that x equal to r times y, and in this case x comma y has norm absolute value of this is equal to x comma r. So we replace x by ry comma y, okay, and this is equal to, so absolute value of this, and this is equal to r times y comma y, absolute value of this, and this is equal to r times the absolute value of r times norm y square. And on the other hand, right hand side, so well, so we can write this as absolute value of r times norm y times norm y, and this is equal to r times y norm of this times norm y, and this is equal to, what is this, ry equal to x norm x times norm y. So equality holds in case equality holds in this inequality, and for case 2, so we consider x and y are linearly independent. Therefore, this implies x is not equal to lambda y for all lambda belongs to set of reals. And this is if and only if x minus lambda y, this is not equal to 0 for all lambda belongs to R. So if this is not equal to 0, so this implies x minus lambda y has norm non-zero and square is also non-zero, and this implies x minus lambda y comma x minus lambda y. So by definition, this is inner product of x minus lambda y comma x minus lambda y. This is not equal to 0. Now using bilinear property of inner product, we have, so this implies x comma x plus lambda square y comma y inner product minus 2 lambda times x comma y. This is not equal to 0. Now we can see that this is nothing but quadratic equation in lambda y comma y. This is coefficient of lambda square minus 2 times x comma y inner product times lambda. So this is the coefficient of lambda, and plus, so this is nothing but norm x square. So here this is also norm y square. So instead of writing inner product y comma y, let me write norm y square. So this is actually not equal to 0, and this is positive. This is strictly greater than 0 in particular. This is also strictly greater than 0 in particular. And this is strictly greater than 0. Though non-zero is suffices. So in particular, this is strictly greater than 0, and this is also strictly greater than 0. So now we can see that the left-hand side of this inequality is a quadratic equation in lambda with no real root. So for every real number lambda, left hand side is strictly greater than 0. That is, this implies the quadratic equation LHS quadratic equation has no real root. And this implies the discriminant of the quadratic equation is negative. So that is, this implies minus 2 times inner product x comma y whole square minus 4 times norm x square times norm y square. This is less than 0, and this implies uh, x comma y has inner product, and square of this is less or equal to norm x times norm y square of this, and this implies absolute value of x minus x comma y as inner product. So absolute value of this less or equal to x norm x times norm y. So which is the Cauchy-Schwarz inequality. So this completes the proof of Cauchy-Schwarz inequality. Now we prove triangle inequality. Now we prove the triangle inequality. Triangle inequality of D2. So here is the proof. So D2 of x comma y square. So this is by definition. This is equal to summation xi minus yi whole square. Summation over I equal to 1 to n. And this is equal to summation xi square I equal to 1 to n minus 2 times summation xi x. Okay, so instead of writing this, let me write. So in other words, so we can write this as norm of x minus y square, and this is equal to x minus y comma x minus y inner product, and this is equal to uh, well so we have to, so let me write what we need to show. To show d2 of x comma y less or equal to d2 of x comma z plus d2 of z comma y. Okay, this is what we need to show. So d2 of x comma y square, this is equal to what? This is equal to xi minus yi whole square summation over I equal to 1 to n, and we may write this as xi minus zi plus zi minus yi whole square. Okay, and this is equal to xi minus zi whole square plus 2 times xi minus zi times zi minus yi plus zi minus yi whole square summation over I equal to 1 to n. I equal to 1 to n. So let me put summation at every place. I equal to 1 to n. Summation over I equal to 1 to n. Now this is nothing but d of x comma z. So d2 of x comma z square, and this is nothing but d2 of z comma y square. And here we use Cauchy-Schwarz inequality, and this is what? This is 2 times inner product. So this is equal to 2 times inner product x minus z. So x minus z comma z minus y, and this is, so absolute value of this inner product is less or equal to less or equal to norm x minus z times norm z minus y. Okay, so this is also, if absolute value is less or equal to this, then this inner product is also less or equal to this. And what is this? This is nothing but this quantity is, so 2 times, so here we have 2, so this is nothing but 2 times, so this is d x comma z, and this is dz comma y. Okay. So therefore, what we have this. So here we have inequality. Now this implies d2 of x comma y square, because the middle term is less or equal to this quantity. So we have inequality here, and this is less or equal to. So now this is what, this is nothing but d2 of x comma y plus d. So this is not y, this is z. d2 of x comma z plus d2 of z comma y whole square, and this implies, so all these are non-negative, d2 of x comma y, this is less or equal to d2 of x comma z plus d2 of z comma y. So this is triangle inequality for d2. Thus we conclude that R2 comma d2 is a metric space. And this metric, this special metric is called Euclidean metric. Okay, this is Rn, is called the Euclidean metric on Rn. So this is called Euclidean metric on Rn. So now let us generate a class of examples, or generate more examples. Generating more examples. So suppose x comma d, suppose x comma d and y comma rho are metric spaces. And x cross y, this is Cartesian product of x and y. So this is equal to, so this is Cartesian product. So this is equal to x comma y, such that x belongs to x and little y belongs to capital Y. So this is Cartesian product of x and y. Now we define few functions. d1 from x Cartesian product with y cross x cross y to R defined by d1 of x1 y1 x2 comma y2. So this is equal to d of x1 comma x2 plus rho of y1 comma y2. So x1 x2 these are in x, so d of, so here is d of x1 comma x2, this is well defined, and rho of y1 comma y2, this is also well defined. So y1 y2 these are in y. And second, we define d infinity with domain this and codomain this, defined by d infinity of x1 comma y1 comma x2 comma y2. This is equal to maximum of d x1 comma x2 comma rho of x1 y1 comma y2. And third one d2. So again domain is the same, and codomain is R only, and this is defined by d2 of x1 comma y1 comma x2 comma y2. So this is equal to d of x1 comma x2 plus, so square of this plus row of y1 comma y2 square of this whole power half. Okay, so now we state as a lemma x cross y comma d1 second x Cartesian product with y comma d infinity, and third x Cartesian product with y comma d2, where d1 d infinity and d2 these are defined here, and the lemma says that these are metric spaces. Okay, so let me remark the proof of this lemma is similar to showing Rn comma d1 Rn comma d infinity and Rn comma d2 are metric spaces. So already how to prove these are metric spaces we have explained, and proof of this lemma is very similar to showing these are metric spaces. Metric. So therefore the proof of this lemma we leave as an exercise. And before stop, let me give another set of examples. So let x equal to the continuous set of all continuous functions defined, real valued continuous functions defined on 0, 1. So this is the set of all continuous functions f with domain as 0, 1, and this is real valued, so that f is continuous. This is the set of all continuous functions, the set of all continuous functions. And now we define, so let me state as a lemma x d1, where d1 of f comma g, where f and g these are continuous functions, real valued continuous functions defined on close to interval 0, 1, and d1 of f comma g, this is defined as f of x minus g of x. So absolute value of this integration over 0 to 1 dx. And second x comma d2, where d2 of f comma g, this is equal to f of x minus g of x whole square integration over 0 to 1 and then whole power half, and 3 x comma d infinity, this is where d infinity f comma g, this is equal to supremum of or maximum of f of x minus g of x, absolute value of this over x belongs to the domain 0, closing interval 0 comma 1. So lemma states that these are matrix spaces. So again, the proof of this lemma is an exercise. Okay, we stop here.